Okay, maybe I'll, since I like to walk, I'll take this one. Also, it's a real pleasure to be with you here today, and thanks for the conference organizers to give me the opportunity to share a little bit what I have been up to lately. So I spent a lot of time at Microsoft working on programming languages, and at some point I said, okay, it's wonderful, but what are the systems that we actually build with these programming languages? And one of the most challenging systems is systems that are distributed and that have to deal with scale. And so I said, okay, I can try to continue doing this at Microsoft, but maybe it's time to change, in some sense, the environment and look elsewhere. So I joined Facebook a half year ago. And if I do my talk well, then I hopefully you explain how Facebook works behind the scene and not only on the surface, because that's exactly what I tried to learn and figure out during the last half year. So I want to tell you a little bit what are the challenges to achieve high availability at scale. So what are the, so my agenda is really if you understand how Facebook works, then I achieve my goal. And it took me quite some time to understand how that actually works. So we'll talk a little bit about scale challenges, about the organization that I joined, that's Core Infra and their objectives. We talk about consistency, replication, and sharding and fault tolerance. Okay, scale challenges. So this is, I show some pictures of Facebook data centers or what's inside the data center. So these data centers are really huge, and there are hundreds of thousands of servers in each of these data centers. But ultimately, they run your bits. So what are the bits that we are running, and what are the scale challenges? So this is public data. Of course, most people know that Facebook is doing pretty well. This is the number of daily active users. And user typically spends around 50 minutes per day on Facebook. So there are 1.2 billion users per day spending 50 minutes on average. That you can translate that back. That means is per second, there are hundreds of millions of users accessing the service. So hundreds of millions of users per second that we have to serve. At the bottom line, there is in some sense another number that's 66% typically. That means is in total, there are probably approximately 2 billion people that are monthly active users on Facebook. So we have to deal with those people, and so they don't fit into one machine. So one of the first graphs, actually I didn't discover it immediately when I joined, but later was this one that I found that tells a little bit the story about the complexity that goes on. So this tells about the networking bandwidth and amount of stuff that we are moving around. So it turns out that if you go back to this slide, you see, there are only 200 million people added from 2015 to 2017. Maybe that's not so much. And so you would think there's a linear, maybe growth curve. Unfortunately, that's not linear. So it turns out that if you interacted 50 minutes 2 years ago with Facebook, then the amount of data that we ship back and forth is approximately the same 2015, 2016. This is the machine-to-person amount. But it turns out that inside the data center, inside these big buildings, we suddenly ship much more stuff around. And so the question is, where does this come from, that there is in some sense a non-linear growth in the demand of networking, and turns out also in compute and storage? Anybody has an idea? Where does this come from? Why is this not, why do we suddenly have the machine-to-machine growth in networking?
You're remembering everything. That means that the amount of stuff that you remember from one interaction grows.
Yes, yes. And in fact, if you add more people to a network, then in some sense, the more connections you have in the network, and therefore everything grows exponentially. And so this is really the funny observation that if you want to grow a social network, you have to deal with exponential growth in demands on your resources. So that's bad. And then in addition, we keep histories much longer, but we have also more demanding services like language translation, which wasn't there 3 years ago, more demanding medias like 360 videos or Facebook Live, where people suddenly there are suddenly 100,000 people watching the same video that's recorded on a phone, and it's all live. So things are growing like crazy. And so the question is, how can we contain and can we build infrastructure that sustains this growth? And how long can we sustain this growth? So obviously, this is a programming language. It's a wonderful community. We build abstractions. And so you build abstractions for operating systems, distributed operating systems, or highly optimized middleware. So, that's the job of my current team. So this is called Core Systems at Facebook. There are many groups at Facebook. So Core Systems is only one. So we don't have to solve all problems. What are the problems, the two problems that this group tries to solve? It's really simple. It's one thing is make sure that the system is always available. And so I'm not the prototypical Facebook user. I rarely use it. But there are people that are almost dependent on it, like dependent on water. And if something doesn't work, they even call the police. So this is a funny Twitter from 2014 when, in some sense, Facebook was down. And people were calling here the Los Angeles Police Department and says, Facebook is down. What should I do? And they said is don't bother. Ask the right guys. But it's really important that you understand is that maybe for us it's not so important as the Facebook, but for other people it really is. And so we want to make sure that we are always available. There's another thing is if people trust us with their life, with all their data, with their histories, then they want to make sure that they have a history even in 2 years from now. So we should never lose any data. And if you think a couple of years ago, there was Hurricane Sandy that wiped out several data centers in New York and came really, really close to 2 data centers of Facebook. So how do we deal with, in some sense, potential data loss? Better we don't have any data loss. And if you look into any textbook and look into from the 100,000 feet point of view onto Facebook, you will recognize there are just 3 standard techniques for building distributed systems. You do data replication to protect against data loss. You do caching to reduce latencies. And you do sharding to do scale. So I came to Facebook and said, I know how systems work. And then I learned I have, in some sense, while I have a rough idea, I didn't actually think about all the other aspects that you have to worry about. You have to think about provisioning. If you build a new system where there's 1 million people, it probably doesn't fit on one machine. You probably need substantial parts of a data center. So how do you get, in some sense, the hardware? What kind of hardware so that you can run it? How do you deploy on 10,000 of machines? And in which way do you deploy it? How does the service discover other services? Because you can't use DNS anymore because that's way too slow if you want to, in some sense, route traffic inside the data center. How to deal with failures, we'll talk about more about it. But then the interesting observation is that actually most systems are down not because of failures, but because of misconfigurations or repairs. And so it turns out that that appears 100 times more often than actually any hardware goes down. It's actually that some repair goes, in some sense, messes with your system. If you think about sharding, that means is you partition, in some sense, your input space. So Barack Obama has a web page, has in some sense an ID. I have an ID. Nobody looks at mine. Everybody looks at Barack's or Trump's or whatever. So that means is the workload is really, really different for the different people. So how do you do load balancing? How do you do coordination? How do you do config management? We run lots of experiments to figure out who is actually interested in which feature, how to do data management, cold storage, warm storage, monitoring, and so on. So building a distributed system is actually, it's the 3 things from the textbooks and the 15 things that nobody talks about, but that makes really your life miserable. Okay, so what did my team do? I only joined half a year, so I can't claim anything of this. They built, in some sense, lots of vertical stacks. So they built, in some sense, a kernel, which has a package manager, service discovery, and at the bottom there is consistent state, because you want to know that you have a consistent state of what goes on in your data centers and geo-replicate it. There is an administration stack for cluster management. And then there are verticals for batch processing, stream processing, monitoring, and ultimately for the social graph, where in some sense the root of all of Facebook. So I will talk a little bit about the social graph and how that's stored and how that's cached and what kind of consistency we will get. And I will talk about Shard Manager. This is in some sense one abstraction that we built in order to deal with all of the other mentioned problems like coordinating repairs and configuration and so on. So data and consistency. So this is a picture of one of the racks with lots of hard disks. So it turns out that now you build in some sense one rack has 1 petabyte of hard disk. It's absolutely astonishing what goes on right now in these data centers, and they're still not enough. So let's look at the main ingredient of Facebook. That's their social graph. Social graph is really just, in some sense, comes right out of the text box. It's a graph with vertices and edges, and it's all typed. And if you see any, in some sense, post, like here from Nathan, that's one of my colleagues, you will immediately can, in some sense, pick it into the ingredients. There's a post, there's a photo that was uploaded from an app. The post was commented on by a user who is an author, and it has a comment, and so on. You can go to the Facebook developer API and actually look at, in some sense, everything that Facebook exposes, exactly how this API looks like. It's in some sense a graph API. So I think for this audience, that should probably be good enough. Let's see how that works inside. So how does, in some sense, how does this service more or less look like? What's the typical ingredients? So Facebook started really as a 3-tier application. There is, in some sense, user interface, there's a web server, there's a master database. But if you want data, if you need replication, and if you need, in some sense, fast, low latency, you have to put in caches. So I will talk about this graph cache called tau that sits actually between the web servers and the master DB. Okay, but that's probably not enough because you can actually search the graph. So maybe there is another service that's called Unicorn, and that caches, again, different parts of the graph. And it caches different because the queries are different, and we want to guarantee low latency. In addition, this graph store is not, in some sense, powerful enough. You have sometimes queries where you have to transitive query something. So there's another edge index service. And it turns out that this guy already stores data and is not only a cache. So it starts accumulating its own data, and there's not only the core data in the master database. If you think about caching, and if you think about timeline as the feature, then of course timeline would actually jeopardize every cache because you actually cache things that's really far out from the past. So again, you build a new service for timeline. You also build a new service for newsfeed. So what happens is that the whole backend actually consists of hundreds of services, all cache and all shard, and some store data. And now the question is, if you have such a complex system, how can you guarantee anything about correctness? I worked on correctness. What do you say about consistency? Is it actually something that's over here? Does it have anything to do with over there? And what can we say about those queries and questions? And if you don't have consistency, what happens? What's the worst thing that could happen? Worst thing might be a privacy violation, but maybe something more innocuous might be that in some sense there is a notification about an event, but the post for that event hasn't shown up. So how can we control this beast of inconsistency in our system when we have so many different services, so many different caches, all developed by different groups, all developed in different languages, all developed and deployed at different times? So that's really the challenge. Can you control this monster inside to give, in some sense, a consistent view of the world to our users? Okay, let's try to analyze the consistency of the social graph and this caching layer tau. And so for that, I want to show you how the architecture inside looks before we can argue about the consistency. So here you have, in some sense, think about 3 regions. Maybe one is in Asia, maybe one is in Europe, and maybe one is in the US. So there's a master, in some sense, region. There's a master for each of the data. And so all the data in the social graph is stored in MySQL. And then there are the squares, and these are caches. These are caches of this tau system. And so we see it's a 2-layered cache system. And so now what we want to do is actually look at how would actually write requests work in the system, and how do we propagate, in some sense, all of the data to the different data centers. So suppose that we have the write request on starting in a web server connecting to a follower cache that is in a different region where actually the master of this data is hosted. So that's the green arrow. So we ask the follower cache, do you have, no, we tell the follower cache, please update this data. It forwards it to the slave cache, which talks then to the master cache, which then talks to master. So that's 1, 3, 4 hops until it hits master. So we write it, and we update everything. So this is good. But now if I wanted to see, in some sense, anything of this, what happens with the other caches and with the other databases that are elsewhere? So on return of, in some sense, the update, I can actually send notifications to the other caches, the caches on the path that I'm actually updating, and says, hey, here's new data, which still leaves, in some sense, the slave databases not in sync. So then I also say, okay, let me replicate the data to the slave databases. And once the data ends up on the slave database, I can, in some sense, update the slave cache, which then updates its leaf caches. And so this is, in some sense, how the core of the social graph and the caching works. So now you can ask the questions, what do you get what kind of consistency model do you get with this architecture? And it's pretty clear there's only one writer, namely that's the master. So you should get something like sequential consistency for the one object that's being written. That's good. If you are in a session in Facebook and you are on one of those web servers and you talk to one particular cache, you should get read after write consistency because you have just written it, and since you're connecting to the same cache, you will read it. And since we replicate the data lazily, but they will be replicated, you would get eventual consistency for the whole system. So that's exactly the model that exists. And now the question is, whenever we talk about eventual consistency and these strange consistency models, how good is it actually for users? How often do they actually see bugs or inconsistencies appearing in our system? And can we quantify it? And so that's what we try to do is, can we actually find out if we would have a linearizable system, how many things would be different? And so, and can we quantify it? So let's try to analyze it. As you probably recall from linearizability, it simply says it's a total order of all operations consistent with, in some sense, the real-time order. And I've shown you the per object sequential consistency and the read after write consistency. And so now what we can do is, let's simply see is, let's take a trace from the real system and we did this 2 years ago for 12 days, and we collected 2 billion requests, and that was a sampling rate from 1 out of 1 million requests, because we have so many. And we tried to figure out what vertices and edges are impacted, what vertices and edges are read and written. And the funny observation is, and it's actually not so funny, it's quite understandable that if you think about the read-write behavior for social networks, it's really skewed. So it turns out that for vertices, these are the objects, in some sense the people, the photos, what have you, you, in some sense, read them 450 times more than you ever write them, right? So typically, you watch photos, you only take it once, you upload it once, but then you watch. And for edges, which are the relations, they are updated more often. You like photos. In some sense, that's why there is, in some sense, a higher write rate than for objects. But it's still 200 times more reads than writes for even edges in this graph. So we took this, in some sense, 2 billion requests and said, can we, in some sense, and we took these requests with, in some sense, time shots when we saw them happening, starting at the edge from the web server. And then we want to see is, can we actually compute whether this trace that we collect, is it actually linearizable, or how often violates it linearizability? And so what we built is a linearizability checker, so which builds a graph, and the vertices are read and write operations, and the edges are ordering constraints. And then we can see whether the total order exists, and if it exists, it simply means it's not cyclic, right? That's in some sense the total order on the graph. And so let's try to do this, and I'll show you how we detect, for example, stale read anomalies. So here are two processes. There is a process 1 and 2, and there's a process 1 writes the value a to the variable x, process 2 writes b to x, and after both have written, process 1 reads again, and it reads a. So that's obviously a stale read. So we'll take this trace that we have actually recorded of all the different requests from all the different clients, and we translate it into a graph, and the graph looks like this. And sometimes it's just the time ordering of those events. But you notice that in some sense we see that the read 1 actually reads the value of that was written by 1 and not the value that was written by 2. If it would be the value written by 2, it would be a legal linearizable order, but this is not. So this should reduce to, in some sense, a cycle. So the way that we do this is we associate the read node with the current write node. So in some sense, we order the graph cyclic. So this has the same edges, but now it's closer together. Now we, in some sense, collapse the read and write nodes, and as a consequence, we get a cycle in our graph. And that's how we detect, in some sense, stale read anomalies. So how many anomalies did we find? It turns out that in these 2 billion long trace, we found 3,628 anomalies on vertices and 12,000 on edges. That means our existing observed trace violated linearizability 0.000399%. So almost not noticeable. That means is actually there are people that see inconsistencies, but it rarely matters. And if you actually go to weaker models like cluster read after write, that's the typical behavior that people see because they're attached to one leaf cache, then it's even better, so they see even less. So it's 0.00006% that they see, in some sense, a violation of our linearizability. So what I want to say is, for the particular case of Facebook, where you have high reads and low number of writes, and where you try to attach clients to leaf caches, normally it works pretty well. So in some sense, it's as if you would have written a much, much better system, but a much better system or more consistent system would have a much higher price to pay in order to coordinate between all the different reads and writes. So efficiency works, and the result is not that bad. But then we wanted to know is, can we actually run this checker all the time? And you can imagine you can't run this all the time because it's way too computationally intensive. So then the question is, can you run a different checker and still check for consistency? And so that's what we did, and it turns out that that's actually a really simple trick. You simply say is you inject reads to all of the caches that you want to know. And then you simply monitor whether any of these caches deviate, so don't have the same value. This is what we call phi-p consistency. And what we'll see is that the increase in network delay or replication or misconfiguration will immediately change this metric. And so let's do this. And here is in some sense how this shows up in real life data. So here we looked at 3 hours of injecting these tests in our running system. And we see that we look at once the replicas are only contained in a region and once they are global. So this is phi of G and phi of R. And of course, within the region, we see in some sense 0.1% inconsistency. And we see up to 0.5% inconsistency globally. Of course, it's clear that globally, the cache contents deviates more than just locally. So this makes perfect sense. In case there is an error, here was an error for, in some sense, the photo comments. We immediately see that this metric spikes until we got it after 4 hours under control, and then it stayed low again. And for photos, it's clear photo comments. Once you post a photo, everybody watches it. And so you immediately see, in some sense, if things go wrong. So it turns out that this simple metric works amazingly in practice. So it's, in some sense, it's just one-time verification. Now we try to understand this. Hey, we have this simple metric, and we have the complex programming language metrics about linearizability and serializability and all this other stuff. How do they relate? They don't relate at all. That's, in some sense, the bad news. But we have, in some sense, still found how we can bound, in some sense, our inconsistency rate, and we have a working model to deal with it. With this, I want to come to my second part, and this is sharding as a service. So now we know how, in some sense, Facebook works, part of the Facebook stack works. Now I want to see is, can we actually use some common infrastructure and help with all of this deployment and provisioning and repairs and so on? And can we build a generic sharding service? And the generic sharding service should shard, in some sense, many different things. It should shard things that where the keys are users. But if we shard, in some sense, a distributed logging system, maybe it should shard the categories under which we should log. If we shard, what else do we have here? If we shard this graph search, maybe it should shard something about the structure of the edges and so on. So can we build such one system, as we heard earlier, to rule them all? And it turns out that it's actually complicated, but we tried our best and it works most of the time. So what's the state space of choices of these generic sharding systems? So you have to understand is how to deal with different keys. If you have systems that have to be consistent, you might use Paxos with primaries and secondaries, so you have different roles. You want to either have an eventual consistence or a strong consistence system. If you shard language translation, maybe you want a replication for Chinese and English to be very high, whereas replication for German is maybe much, much smaller. You want to know the affinity. If most of the users are in Asia, maybe you want to see that, in some sense, the shards of the Asian users are actually in Asia and about the European users in Europe. So that's the affinity. Sometimes your system is dependent has storage as the dominant resource, and sometimes it's compute, and so on and so on. So you have these monster choices, and you still want to build one system in which you can, in some sense, distribute the workload over your fleet. And so you can use this sharding as just a scheduling or load balancing problem, and that's what we did. So we simply says, okay, hosts or application servers have capacities, replica have resource demands, and then the only thing that you want to do is build an assignment. So when you build solvers, you know how to do that, and there are linear integer solvers that do that well. You have constraints that you can never have more demands than on one machine than the machine has capacity. But now we have also lots of other constraints that have to do with failure tolerance and with affinity. And so the question is, how can we deal with that? And how can we rebalance? So we have this language. We have a language for these constraints. One is the simple one for the host constraints. I'm not going there. But then there is a language how you can specify constraints over trees. And it turns out that that actually works pretty well, because now you can simply say, okay, if certain shards should be allocated in this kind of fault domain, in this region of the world, or on this rack, then you can specify preferences. So all these shards are allocated here. You can say spread if you want to have failure tolerance. You want to make sure that in some sense the replica works maybe in a different region or a different cluster. And you have co-location. You want that this database server actually works very close together with maybe this business logic server for this business logic. So you have three kinds of constraints on these trees. And it turns out that you have exactly 3 dimensions on trees. So it works beautifully out, and you can have a little algebra in order to express those location constraints. And what's furthermore really nice is you can use then all the tricks that you've learned in programming languages and static analysis to compute summaries of what should go into a tree. You can do some pre-computation, and then you can solve these constraints greedily and really, really fast. And so let me show you some results. This has been implemented in the sharding as a service. The architecture looks very abstract like this. You have a shard manager that controls, in some sense, the responsibility, which shards are on which application servers. The application clients connect to the proper application servers using the service discovery system. So the shard manager updates the routing table all the time based on load balance updates, and the service discovery pushes, in some sense, the routing tables to the application clients, which then can connect to the right application servers. Not going here. So how does that actually then work? So this is, we have hundreds of services on Shard Manager. They have up to 10, 20, 50, 60,000 servers. They have hundred thousands of shards. Think about we do micro-sharding, so we can't shard every user, but we group users together much closer, and we still have hundred thousands of users that are then collected in shards. The median are approximately 100 shards per server, but it turns out that because of the very different demands by very different people, the amount of load is very different for my web page as for Obama's web page or whatever. And so we sometimes see a factor of 100,000 difference in the resource consumption from the different services. So 100,000, that means is we can't use containers or anything like that. So what we decided is everything runs as multi-tenant service so that we can put them all close together. And then there are servers that have just one shard, and there are servers that might have 10,000 shards. What we wanted to achieve is that there's only a small deviation in the load in total, and this is what the graph on the right shows. What we also wanted to achieve is that the system is failure tolerant. So if a server is suddenly down, we move automatically the shards from that server away. And so this is the first graph, which shows that when a server fails, we still see a minimal impact. But if there are 100,000 shards from one server and just one server dies, then there's only shards impacted. So in some sense, typically the impact of any server going down is relatively small. The graph below shows if we actually know that the server will go down, we can take proactive action, meaning as we can move the shards ahead of time, and there's no impact whatsoever. So summarizing, sharding as a service actually works. It really is an important enabler for building scalable, available distributed middleware. We only know of 2 systems that have been proposed, one by Twitter called Helix, and Google has one published last year. But maybe this is actually really deserves more investigation how to do this really well. With this, let me conclude. And what I've learned in the last half year is that building distributed systems at scale is really complicated. And it's actually complicated for all the things that you don't think about. The immense load heterogeneity that we see, and sometimes the huge difference between reads and writes about those objects that are monstrous, that have 100,000 connectors, and others that have none. The behavior composed by many different services that together have to give a consistent view. Each one is actually simple, but together get a consistent view, where you have different caches, different sharding schemes, and different teams involved. So a funny story, for example, there's one data center that takes down, in some sense, a server for maintenance. And in a completely different part of the world, there's another data center where the organization also takes down a rack for changing the top of rack switch. It turns out that they actually use exactly the same services. They don't know of each other, so you have to coordinate the world around your service to protect yourself against all these things that happen constantly. And so this is maintenance dominates failures by tens of factors. And I think if you look at the latest Amazon S3 glitch, it was also a maintenance issue. So this is really underappreciated in our community, that these boring things really make a big difference whether your system works or not. And the other part that I never really recognized, I typically worked on multi-core systems. That's where everything is really close by. But if you think about geo-replicated systems where part of your data is in Europe and part is here, you can't trick physics. And sometimes you have to deal with the latencies that are there. So I've shown you 2 scenarios, the social graph and the middleware stack. And all in all, you can still build those systems. It's just not as easy. But we found that we built systems that have a high degree of consistency. We introduced novel runtime techniques, and we actually can build sharding systems that work like, in some sense, fundamentals of building distributed systems, whether they are monitoring systems, pub subsystems, batch systems, or graph search. With this, I want to conclude. Thanks a lot for your time, and I'm happy to take any questions.
So thank you very much. We have a microphone down there. So if you have questions, please step to the microphone and go ahead. Sophia is on her way. No, taking pictures. Yeah, Doug.
Hi, great talk. So presumably all of these little caches have their own consistency models.
Yes,
and so has anyone tried to formally show they have any property whatsoever?
No, not to my knowledge. I should say is I should quantify everything. I'm there for half a year. I think I'm a quick learner, but the company exists for much longer, so there might be wonderful pockets, but I haven't found them.
It's terrific empirical evidence that they're not too bad.
That they're not?
That they're not too badly composable.
Yeah, yes. No, I think it's so people really take, in some sense, a lot of care and pride in building these systems. But what you have seen, the growth was so dramatic that it's really trying to catch up or slowly be ahead of the curve. But in some sense, the wonderful thinking that we do in research, where we think 5 years out, there's no time for it in some sense. So one thing that I'm here is maybe to encourage you, work on distributed systems. It's really important. It's our future. And second, if you don't know where to want to work, there's great companies all over the place. Facebook might be one of them. I think we will hire any one of you in the audience to address some of these issues.
Thanks for the nice talk. If I understand correctly, you've only checked linearizability on a per object basis. Is that correct?
That is correct. So we looked initially whether we can do a better job, but due to the scale, we couldn't. So it's everything is just local.
So you don't have any estimate how much of the imprecision could be due to that?
No, I don't have any estimate, but maybe we can take it offline and have a more technical discussion offline to see what we could do.
If I may, one more general question. So the 15 issues about which they don't write in textbooks, is it the same for Microsoft and Facebook, or there is something in Facebook that makes it more complicated?
Okay. So Microsoft and Facebook. So what I've been a long time at Microsoft, was close to my heart, like my new job is also close to my heart. And so what I see is that the customer profile is very different. So in Facebook, everything you do immediately scales out to millions, 100 millions of users. So in some sense, some of the check-ins that I made impacted probably all of you in such a short time. And Microsoft actually tries to, in some sense, has a different business model where they try to, in some sense, do the best for whatever. Coca-Cola is a big company, or there's other big companies, but also many smaller companies. So the scale issue doesn't immediately arise. It eventually arises because they want to have more and more bigger enterprise customers, and they're coming, but it's not where they started in their cloud strategy. It was in some sense first getting the medium-sized, the ones that are willing to take risks. The bigger the people are, or the organization are, the less likely they take the risk to move into the cloud. And so they have a little bit more leeway. Whereas once Facebook puts something out, it's immediately distributed worldwide, and therefore it hits you hard with the scale requirements. It's not that I think it's, in the end they will end up in exactly the same place, but due to their policies, it behaves differently.
Thank you.
Okay, you talk about consistency and show that you have these 4 nines of consistency.
Yep.
My question is, how important is consistency? I mean, personally, I've never heard of a Facebook user gripe about a consistency problem. And so is 4 nines way above what you actually need to be, or does it matter, or what?
I think there are 2 questions. One is, if you have a linearizable system where in some sense you have the notion of time built in, it's much easier to understand for developers and for users. But as long as users are only attached to, in one session, to one cache, they never see in some sense that the system might be
exactly
inconsistent. So what I wanted to say is, I think it's something that we as a community strive for, but the reality, the users normally don't experience it, and that's why they don't care.
And so my question is also, have you investigated whether there are any users who notice or care?
Yeah, so
have you asked users about it or done some surveys?
So there are, I can't answer that, I can investigate, but I can tell you is, not everything runs on eventual consistency. If you do logins, for example, in some sense all logins are in some sense made sure that they are run with consistency, so there is no caching involved in all of these levels. So there is a conscious choice inside Facebook where you in some sense trade a better latency, better availability for consistency.
Thank you.
But it's a conscious choice.
So my question is also about consistency, and I was wondering, the first measure that you did it only for a limited amount of time.
Yes.
Do you know whether that was representative? Can it be that at some point when more systems were down, it was much worse? First question. Second question, you said that the 2 measures are unrelated, but are they totally unrelated, or does one give an upper bound for the other module or some multiplication or something?
Yes. questions. The first one, the trace was taken in 2015. I think it was a sampling rate 1 out of million for 2 days from application servers spread all over the world. So I think it's probably realistic by having collected 2 billion requests and their correlation. Things change over time. And since we can't run this expensive experiment all the time, that's why we invented the second measure. And now the interesting question is, that was your follow-up, how does it actually relate? So if you would think is you would write a new service, and this new service would do nothing but do exactly what this measure would do, then you would suddenly see, because this measure shows that you would have a much higher inconsistency. But since it's artificial, no user looks concurrently at all caches. It's, in some sense, it's an upper bound on how bad the system can get, but not a lower bound. And then the other one was a trace, so that's then a lower bound. Thank you.